Hi, welcome to the Sedimentary Rock Lab identification tutorial for physical geology. Before you start on the lab, you will need to do the reading in the textbook and visit the lectures and get a basic understanding for what are sedimentary rocks, what are sedimentary processes, how to identify sediment. Also, before starting the lab, you need to make sure that you have the materials that you need. You will be looking again at your rock and mineral kit that you purchased, and you can see the list of sedimentary rocks that are present. So make sure that you have the correct number of sedimentary rocks, and they each are numbered. And then you'll also be using some of the tools that you used when you were identifying minerals in the mineral lab. For example, the glass plate will be helpful when you're trying to determine the hardness of some of the rocks. Your hand lens might be helpful to get a close-up look and trying to determine sediment size, for example. And also your little vial of hydrochloric acid will be useful if you are trying to determine if any of your rocks have the composition of calcium carbonate. So, as you know, sedimentary rocks are rocks that form near Earth's surface or at Earth's surface. Often they're formed because there are fragments of pre-existing rocks that exist because of the whole parts of the sedimentary cycle, from the weathering or breaking down of rocks, the erosion and transportation of the sediment, and then eventually the sediment gets deposited somewhere and gets lithified, which means it gets compacted and cemented together to form a solid rock. But sometimes sedimentary rocks also form without all of those steps. It could be that there are minerals that form from precipitation from a watery solution. Often also sedimentary rocks can form from organic material that kind of goes through the lithification process as well. So that means that there are two broad classes of sedimentary rocks. There are clastic sedimentary rocks. Clast is another word that means fragment, so you can think of a piece of sediment as a clast. So if you hear the term clast, it could be it could be used usually interchangeably with sediment or fragment. And then there's the other category is chemical. Sometimes the rocks are specifically referred to as biogenic or biochemical. But chemical rocks, generally speaking, are rocks that form from ions precipitating into minerals from a watery solution. If the bio root is used, or the word biogenic, then that means that there were also like carbon-rich materials that the carbon had been preserved through special processes, and the organic material becomes lithified or becomes an inorganic substance, and a biogenic or biochemical sedimentary rock. So when we are identifying sedimentary rocks, the first question that we want to ask is, are we looking at a clastic sedimentary rock or a chemical/biochemical sedimentary rock? To determine if you're looking at a clastic sedimentary rock, you want to determine if it's a type of rock that forms from sediment, pieces or class of pre-existing rocks or minerals. And so if you've determined that, then the first criteria that you want to ascertain when you want to identify your clastic sedimentary rock is what is the size of the clast? What is the size of the sediment that is making up the sedimentary rock? Then you can further define the rock or identify the rock by looking at other factors. Sometimes it's useful to look at the composition of the clast. For example, there are many types of sandstone. Sandstone is made up of sand-sized fragments, sand-sized sediment, but there are different classes of sandstone. For example, there's quartz arenite, which is a sandstone where the composition of the sand is largely quartz, but there might be something called like a lithic sandstone, where there's larger sized pieces of sand that are actually, some of them are made up of fragments of rocks and not just single minerals. And other things you might need to look at are sorting, like how uniform in size is the sediment, and things like angularity or roundness of the particles. So keep in mind that when you're looking at these factors concerning the clast, you're not looking at the rock as a whole, like the shape of the rock. You're looking at the shape, composition, sorting of the sediment that make up the rock. And then sometimes it becomes useful when you're identifying clastic sedimentary rocks to look at the nature of the cement that's holding the clast together. So for example, in this picture, we see that there's large pieces of sediment, and there's kind of some finer grain material holding that sediment together. That can be considered the kind of cement for this. Whereas a sandstone that has mostly sand-sized particles, the cement is much finer in size, or not clastic in nature at all. But it could have different composition. Usually it's going to be kind of a silica rich, but it could also be like a carbonate sediment, so it would react to acid. So sediment size, there's a chart that talks about sediment size, and you'll find this in your lab. There's three broad categories of sediment size. Gravel, which refers to particles that are 2 millimeter in size or greater. And then you could further define gravel size as granule, pebble, cobble, boulder, based on the size, the average diameter size of the sediment particles. The next smaller size of sediment is sand. So sand refers to not a composition, not what the chemistry is, but the size of the particles. And there's a range of sand size, but we all are familiar with sand size. We pick up sand at the beach and hold it in our hand, feel it between our toes. But there's actually a range of sand size. Coarse sand, or large grain sand, is up to 2 millimeters in size, and so it's kind of bigger chunks of sand. But sand can be quite small in size. It can be like something like close to 0.5 millimeter in size. And the two sizes below that, silt and clay, again, these refer to size, although clay is also a class of minerals. But these refer to size. They can be kind of lumped together as mud-sized sediment because when we think of mud, it's usually this size sediment that what mud is largely composed of. So silt and clay are so small in size that we can see them, but we cannot pick them out individually. So for example, if I have this container with sand in it, and I pick up the sand and I look at it, I can see the sand as a whole, but I could also kind of separate out the individual particles, and I could see the separate particles. And using the hand lens might be helpful, but I can definitely see them with my naked eye. If I pick up another sample of sediment, and here I'm seeing some kind of gravel-sized pieces, but I also see there's some finer material here. So for example, if I were to just pick up some of this by putting it on my finger, well, I can definitely see it. It's on my finger, but if I try to pick out individual particles, I realize I can't do that. They're too small in size to differentiate. So how do we determine if we're looking at silt or clay? One of the tests that geologists often use is the way it feels. Clay is very, very fine grained, very smooth, and so if you rub it between your fingers, you don't feel much of a grit. Whereas if it's silt size, it feels a little bit gritty between the fingers. Not as gritty as sand, but still gritty, so I'm feeling mostly silt here. When you're looking at clastic sedimentary rocks and they're composed of mud-sized particles, you're not going to be able to see the particle size. It's just going to kind of look all the same. So there's a couple of little tricks to distinguish between those two grain sizes in rocks. Here's just a picture of some other things that might vary in the clasts of your clastic sedimentary rocks. Angularity refers to kind of having sharp edges or corners on the rock, so it doesn't refer to like a shape. It's just the sharpness of the edges and corners. Roundness does not mean that it's spherical in shape like this, just that there's not sharp edges or corners. And so if we think of the sediment as being transported some distance, maybe along a stream, the longer it's transported, the more rounding occurs. Sorting refers to the uniformity of grain size. So very well sorted sediment might be all sand size, but further than that, it might be all like coarse grain sand, or all fine grain sand, or it might be all pebble size, or something like that. So poorly sorted sediment is composed of all different sizes. So, for example, glaciers have a tremendous amount of energy. They transport a lot of sediment, but they don't distinguish between fine-grained clay-sized sediment and huge boulder-sized sediment. So when they deposit their sediment in an environment, they leave behind very poorly sorted sediment. Whereas wind has a very narrow range of energy. So a wind will carry, silt and clay-sized particles far away. It can't move anything larger than usually about a medium grain sand, and then it can't move that very far. So in a wind-blown environment, dry wind-blown environment, you usually get very well sorted sand-sized particles. And then there's other things to think about, like this is a collection of sediment in a high energy environment, and we see all different, not just different sizes, so it's poorly sorted sediment, some angular pieces, some rounded pieces, but we're also seeing the composition of the sediment varies. Like, for example, this is the mineral feldspar, this is mineral quartz, and these are lithic fragments, meaning they're just rocks that have a variety of sediment. And as you've learned when you're learning about weathering, that especially chemical weathering, that a lot of minerals will break down into other substances over time. So you don't. So in an alluvial fan deposit, this is a place where sediment maybe accumulates close to the source, and so the minerals don't have time to change composition so much. So if you see a rock composed of these types of materials, then you know that the sediment wasn't transported very far, or wasn't a very wet environment before it became lithified and turned into that sedimentary rock. In this sample here, we see only quartz, which is very resistant to chemical alteration. It's rounded, it's well sorted, it's smaller in size. So that tells us a lot about what happened between the point when the sediment was created, between the weathering and when the rock actually was lithified. So here are, the next few slides are some pictures of clastic sedimentary rocks, and I broke them in kind of three main categories: fine-grained clastic rocks, sand-grained and sand-sized grain, and anything larger than that. So fine-grained clastic rocks, again, you're not going to be able to pick out the particle or clast size in the rocks. So because the clasts are too small to be differentiated from each other with the naked eye. But the siltstone should feel a little bit more gritty, not as gritty as sandstone. If you were to be able to kind of break off a small portion of the rock and kind of grind it up into a powder, you should feel a little bit of grit. Whereas a mudstone or a shale is made of predominantly clay-sized particles, which only settle out in some very quiet environments. Then if you did the same thing, broke up a teeny piece and pulverized and felt it between your fingers, it should feel like kind of almost like talcum powder, like really smooth. Another trick that geologists use is trying to differentiate between a siltstone or a mudstone is kind of taking a little bite of the rock and grinding that between your teeth, and if you feel the grit, siltstone; if you don't feel grit, mudstone. So I'm not saying you have to bite your rocks, but just so you know, we use all of our senses when we're trying to identify rocks. So the difference between mudstone and shale is that shale actually shows a layering. So I said that the clay that makes up both mudstone and shale will only settle out in very quiet, watery environments. And so that settling or deposition of the clay can happen seasonally, and the composition may be slightly different from season to season, and so that might impart kind of a layering in the rock, and that might be visible as lines in the side of the rock, or it might be visible because you can kind of see it breaks a little bit in a linear fashion, so it looks like a flat rock. It might even kind of break into flat sheets or somewhat flat. And then sandstone is composed of mostly sand-sized clasts. Again, there's a lot of variety to sandstone. In this picture here, you're seeing sand that was deposited probably in a watery environment because it's very very horizontal layering, and it's probably seasonal changes into the influx of sediment that's being deposited, so you see different colors based on the different chemistry of the sand um, and other particles that settle out. This is another sandstone here in the bottom right of the slide. And you see there's kind of more variation in the size of the sands, and so some fine-grained sand, some coarse-grained sand. There might be different, there's obviously different, composition of the sand size class. Coarse-grained clastic rocks have some component of them, or a significant component, that is composed of larger than sand-sized particles, so pebble or gravel-sized particles, I should say. So that means that the rock is poorly sorted, or the clasts in the rock are poorly sorted, a variety of size. So even though there are large fragments, the material that kind of cements it together is going to be finer grained material, therefore poorly sorted. So there's kind of two main coarse-grained clastic rocks. There is breccia and conglomerates, and they can be differentiated by the angularity or roundness of the clasts. Again, do not look at the rock as a whole. Look at the particles that make up the rock. Yet you do see some, kind of somewhat sharp edges. For the most part, these are fairly well-rounded. That tells us that before this material was deposited, it was probably tumbled in a stream or moved some distance so that the kind of edges and corners broke off before this rock was formed. In this one, this rock formed probably closer to the source. The clast particles in it weren't transported far, so they still have the very angular nature to them. So conglomerate and breccia. And here is a picture of a clastic sedimentary rock. And I'll let you kind of take a look at it and try to decide what type of rock this is. So first of all, if we look at a sedimentary rock, we try to determine if we're actually seeing sediment particles or clasts. And therefore, if we do, we say it's a clastic sedimentary rock, not a chemical sedimentary rock. And then this next thing we're going to ask ourselves, what size sediment are we looking at? And from there, we can identify the rock. So chemical sedimentary rocks form from precipitation of minerals from water or from organic remains that undergo lithification, some alteration, so they're no longer organic. So this is a picture of limestone. You can see it forms in a layered way. So this was formed from must have been previously, the setting was a kind of shallow, warm, carbonate-rich sea. And so you have marine organisms that use the calcium and bicarbonate ions in the water to form their shells and hard parts, and all of that material accumulates on the seafloor, and over time, through a couple of different means, sedimentary rocks can form. So this is a picture of limestone, which is a chemical sedimentary rock that's calcium carbonate in composition. So there's a variety of settings in which chemical sedimentary rocks form. It can be in shallow environments where there's high evaporation rates, and so that leaves behind the solid precipitates from the water. As the water is evaporating away, the ions precipitate out and form minerals in a chemical sedimentary rock. This is a picture here. If this is limestone, that means it's a marine environment with a lot of carbonate material. But there can also be marine environments where there's a lot of silicate material, so you'll get chemical sedimentary rocks that form, but the composition of the rock will be different. It will be more like quartz. It will be more quartz-like. In other environments, one example is if you have a subtropical swamp, there's a lot of organic material that's constantly growing and dying and being kind of buried with inorganic material. If it's a kind of a warm environment, then there's not a lot of oxygen introduced in the buried remains, watery environment, and so not a lot of decomposition takes place, and so the organic material gets preserved and gets buried and kind of cooked until eventually it becomes a biological or biogenic chemical sedimentary rock. And here's a picture of a few different types of chemical/biogenic sedimentary rocks. So in order to identify sedimentary rocks that are not clastic, you just have to kind of be able to recognize them. So in your lab, there are charts that explain the characteristics of different chemical sedimentary rocks. For example, if we could look closely at this picture of this rock, we can see that it looks like there are clasts at first glance, but if we recognize that these are very cubic in shape, maybe they salty in taste, then we realize that we're looking at halite, which is a mineral, basically salt. And so this is an evaporite rock. This formed from evaporation of water as the sodium and chlorine combine to form the mineral, the salt mineral. And so this is a chemical sedimentary rock. This is a rock. It's hard to tell exactly what it is until you start maybe recognizing that when this rock breaks, it breaks kind of in a fracture, similar to the way quartz does. Has sharp edges. It's a pretty hard rock. If we use our glass plate, we can see it's harder than glass. Both of those things sound similar to the mineral quartz. So perhaps it's a chemical sedimentary rock that formed in a marine environment where there's a lot of silicate material present. And this would be an example of chert, which fits that characteristic. As I described in subtropical swamp settings, you might get coal forming, organic, which is an organic, from organic remains. We say this is a biogenic sedimentary rock. And how do we recognize that it's coal? We can't just rely on the fact that coal is dark in color. It can be black. It can be really shiny. It can be less shiny. It can be kind of a reddish brownish color. But one characteristic of coal is it usually is very low density rock. And so these are just a few of the chemical/biochemical sedimentary rocks. Again, in order to identify them, if you recognize that the rock you're looking at is not clastic, then you just have to kind of read about the other types of sedimentary rocks and maybe do hardness tests. You know, if you think it might be like a limestone, a variety of limestone, which includes chalk and coquina and other limestones, then you might start to recognize, well, those are rocks that are formed in a carbonate-rich environment. So the dominant mineral in the rock is calcite. It was really easy to identify calcite in the lab once we realized that it's very reactive to dilute acid. So if you think you're looking at that type of a rock, you could put a drop of acid on it and see if it reacts. Okay, well, enjoy identification of sedimentary rocks, and feel free to ask me any questions that arise during your completion of the lab.